Okay, so let's consider the following question. Suppose A, B, C are the sides of a triangle. Prove that A squared times B plus C minus A plus B squared times C plus A minus B plus C squared times A plus B minus C is less than or equal to 3 times ABC. Now, this question showed up on 1964, which was the 6th IMO, and it was problem number 2. So it was a medium difficulty question. So just looking at the question, one thing that we can notice is that it says that ABC are the sides of a triangle, but in what you're trying to prove, it's just an inequality, and it's not really using any properties of the triangle, which is A, B, and C, right? It's just using the side lengths. And we could actually make it just totally separate from geometry if we wanted to, right? Because if ABC are the sides of a triangle, all that means is that it's going to satisfy the triangle inequality. So I can say, I could reword this question if I wanted to. It's like, suppose A plus B is greater than or equal to C. Equal to case, I guess we can talk about being like a degenerate triangle, but you can also just like have it A plus B greater than C. It doesn't really matter. Then you can have like B plus C greater than or equal to A and A plus C greater than or equal to B. So you could say, suppose these three conditions are true, then prove this thing. Oh, and A, B, C are greater than 0. So if we wanted to, we could completely remove the geometric side of this question. And there actually are solutions involving that, right? Like just completely getting rid of pretending that ABC are sides of a triangle, just doing it synthetically. I know there are some solutions where you do clever substitutions, and then it turns out just to be pretty easy application of AMGM. Okay, but today I wanted to share a really, which I thought was nice solution to this question that actually uses the fact that they are sides of a triangle. So I'll just give you guys a couple seconds so you can pause the video if you want to just think about this question. How are we going to try to relate some of the geometric things, some geometric properties of a triangle into this really messy looking equation? All right. So now I'm going to start talking about the solution. So like if you still want to consider the question, then like just pause right here. But yeah, let's continue. So the first thing that we want to do is, well, I want to motivate something first, right? So we see we have a bunch of squared terms, right? A squared, B squared, C squared, and we have this thing that's like A plus B minus C, so we have some minuses and stuff. And if we try to rearrange, we could get something like this, right? So we have A squared B plus A squared C minus A cubed, and then we could try to expand the entire thing. But what we can quickly realize is we can just take a look at things that are factors of A. So like A squared times A, or B squared times A, or C squared times A. So if we try to look at it like that, then what we would get is A times B squared plus C squared minus A squared plus B times C squared plus A squared minus B squared plus C times A squared plus B squared minus C squared. Now, this might start to become familiar, right? When we have three squares kind of looking like that, that really reminds you of the cosine law. So in the cosine law, it says that if I have a triangle, and let's just say it's a random triangle, there's A, B, C, and then of course the side lengths are opposite of the angles. So it's going to be A over here, B over here, and C over here. So if we wanted to get this kind of a structure, the application of the cos law would be a squared is equal to b squared plus c squared minus 2bc cos of angle A. So then we can do a little bit of rearranging and we can get 2 times bc cos of angle A is equal to b squared plus c squared minus a squared. And we can get a really similar thing for the other two. So we can say, similarly, we can have that. Just taking a look at this one, we're going to have 2ac cos b equal to the expression that we have. And then taking a look at the final bracket, we're going to see that 2 times ab cos of c is equal to a squared plus b squared minus c squared. Okay, so we have these equations and we can just plug it in. So I'm going to take a factor of 2 out front and we're going to get ABC cos A plus ABC cos B plus ABC cos C. We want to show that this is less than or equal to 3ABC. Aha, and that's really nice because all of these terms in here have a common factor of ABC and so does the product on the right. So what's really nice is we can now just simplify it and make it cos A plus cos B plus cos C is less than or equal to 3/2. And we've reduced the problem to just showing this. I'm pretty sure that this is a known inequality, but I actually haven't been able to find it online. So I can sketch a part of my proof for this here. So what we can do is we can just draw a triangle. Let's say this is A, B, C. This is A, B, C. And let's drop an altitude. Okay, so this is angle B and this is angle C. So we can say that A is equal to C times cos B plus B times cos C. So this should be a lowercase. Okay, so C cos B plus B cos C. And then similarly with the other ones. So we can say that B is equal to A cos C plus C cos A. And C is equal to A cos B plus B cos A. So now if we're going to add up each of these, we will get that A plus B plus C is equal to A times cos B plus cos C plus B times cos A plus cos C plus C times cos A plus cos B. All right. So we can kind of see that we have this ABC and we have this ABC on the left side. So let's just say that S is the sum that we want, cos A plus cos B plus cos C. Okay, so if we substitute this in, we can get A plus B plus C is equal to A times S minus cos A plus B times S minus cos B plus C times S minus cos C. And then here we can expand everything out so we can get A plus B plus C is equal to S times A plus B plus C minus A cos A minus B cos B minus C cos C. Do a little bit of rearranging and we can get that S minus 1 times A plus B plus C is equal to A cos A plus B cos B plus C cos C. And all right, so what we can actually do here now when we're looking at this, we want to prove that it's less than or equal to 3 halves. Now, okay, so just looking at it, one thing that we can notice is that, let's just say without loss of generality, that C is greater than or equal to B is greater than or equal to A. So something that we can notice is that the coses actually go in the reverse order, right? Because if you can imagine a cos graph, right, we know A, B, C are less than or equal to 180. So if you take a look at the cos graph, up to 180 degrees or pi, or I shouldn't put a slash, so 180 degrees, I'm going to put, oops, or pi, it's always a decreasing function. And that means that cos A is greater than or equal to cos B is greater than or equal to cos C. Okay, and now let's consider something. Okay, so let's say that I took these three numbers A, B, C, and I had to multiply each of them by one of cos A, cos B, or cos C. All right, so the expected value, oops, the expected value of this kind of experiment, remember I'm choosing one of these, and I'm multiplying by one of these, and then I'm doing that 3 times, and they should all be different. So like if I put C with cos A, I can't put A with cos A anymore. So I'm just taking, so it should kind of look like this, where we have like A times cos something plus B times cos something plus C times cos something, but we're not going to repeat anything. So each of them is going to show up at least once, or sorry, only once. So the expected value of this is just going to be the average of everything, right? So we take a look at the average of the first set times the average of the second set. But since we're doing that 3 times, we have to, at the end, multiply by 3. So we can cancel out one of the denominators. Okay, now how do I get the minimum value? And what's actually surprising is that, or maybe not so surprising, the minimum value that you can get from this is by matching up the largest of one set with the smallest of the other set, and matching up the second smallest with the second largest, and so on. And that may be kind of unintuitive, but you can just kind of think about it, right? If I want, like if I'm doing a multiplication, I want to try to put the bigger ones together because that means those two are going to really make a huge number that's going to contribute. And then if I take the smaller numbers, right, if I take a smaller number multiplied by a bigger number, then that's going to like really take down the potential of the bigger number. So yeah. So the minimum value is actually C times cos C plus B times cos B plus A times cos A. And here's where we can introduce our inequality. Because the minimum value, it has to be less than or equal to the expected value, right? So therefore, I can say that the minimum value has to be less than or equal to A plus B plus C over 3 times cos A plus cos B plus cos C, but remember that we replaced with S. And remember, the minimum value actually was the same thing as S minus 1 times A plus B plus C. So let's just sub that in. A plus B plus C times S minus 1. And here we can notice that a plus b plus c is always positive, right? Because they're the sides of a triangle. So we can just divide both sides by that and multiply by 3. So 3s minus 1 less than or equal to s, 2s less than or equal to 1. And there we go, s less than or equal to 1/2. Oh, sorry, I made a small mistake. So it should be s minus 3. I forgot to carry the 3 over. I was going to say something was weird. There we go. So s is less than or equal to 3/2. That makes sense. Okay, and there we go. So that's how we can get that. This is that's how we can get that s is less than or equal to 3/2, and that way we can finish the question. Now, I'm just going to do a bit more of a rigorous proof, right? I mean, you might not buy the fact that to get the minimum value, you match the highest one of one set with the smallest one, and then the second highest with the second smallest, and so on. That might be completely unintuitive, and maybe you're still unimpressed by my explanation. So I'm going to provide an alternate explanation, which is a lot more rigorous. So to do this, I'll actually just go to the side because it's kind of like a side note. Okay, so let's just take two numbers first in each set. So let's say we have a, b, c, d, and say a is greater than or equal to b, and c is greater than or equal to d. Okay, so what I want to show is I want to show that, well, there's really only two ways to match up the numbers here, right? AC and BD, and the other one is AD and BC. So I want to figure out which one is bigger out of the two. Okay, so what I can actually do is I know that A minus B times C minus D is greater than or equal to 0, right? Because A minus B should be non-negative and C minus D should also be non-negative. Right, so if I expand this out, I can get AC minus AD minus BC plus BD greater than or equal to 0. And here, if we do some rearranging, there we go, AD plus BC. So we can find out that for two numbers, we always want them to have the two biggest ones and then the two smallest ones. All right. And you may be just asking, like, how did you magically come up with this? That's because, like, when I'm doing it, I'm starting with this statement, and then I'm going backwards, basically, and I'm trying to figure out, okay, how can I factor it, maybe? Because, well, I mean, it looks kind of factorable, and that's how I ended up with that. And then to complete the proof, we're just going to say, let's say I have sets, and I have numbers n1, n2, n3, and they're all greater than or equal to all the way to like nk, then m1, m2, all the way to mk. All right, so then what we can kind of say is we can say, just take a look at n1 and the person that we're matching n1 with, let's say over here, and also n2 and the person we're matching n2 with. Okay, so if the person we're matching n2 with, the index is smaller than the one that we're matching n1 with, then that's good. Then we have this kind of a situation, right, where we have BC times AD, and that's the minimum. So that's okay. But then the problem arises if I have, say, Ni times, so let's say we have Ni plus 1, and the way we're multiplying it, we're taking Ni times, let's say, like Mj over here, and then let's say we're doing like Mj plus 5. Then this is problematic because, right, from just looking at the two variables, I can actually do a swap here. So I can say, okay, don't multiply these like this, actually multiply them like that. And so anytime where I'm running along the n column or the n row, I have to go backwards along the m row. And anytime I don't go backwards, I can actually improve that by going backwards. So I just keep improving the sum to make it as small as possible until I can't improve it anymore, which is when it just keeps going all the way in one line. So that's kind of that explanation. All right, but then just to finish, I'll write out the entire proof just like I would on a contest. Because on a contest, I wouldn't write like, I'm thinking this and then I'm thinking that. No, you want to start with a statement and then you want to continue on. All right. So if I was on a contest, I would probably start here. I would say let S is equal to cos A plus cos B plus cos C. And then I would use the triangle and get this result, solving for S and showing that S is less than or equal to 3/2. But I think that it's well known enough. So what I'm going to do is I'm going to start with, and I'm just going to say let A be opposite A. So let's say let point A be opposite of the side length A. Let B be opposite of B and C be opposite of C. This is just like safety. I don't think you really need to write this every time because it's pretty standard how to write ABC in a triangle. Okay, so we can say that. Note that cos A plus cos B plus cos C less than or equal to 3/2. Then we can say from cosine law, cos A is equal to, and then we can just take a look at what it was equal to. So it would be equal to b squared plus c squared minus a squared divided by 2bc. So let's just write that down. And then we would just write down each other one, but I'm not going to write it down. Okay, I'm going to say subbing in, we get that b squared plus c squared minus a squared over 2bc plus, this would be a squared plus c squared minus b squared over 2ac plus b squared plus a squared minus c squared over 2ab less than or equal to 3/2. Then we can just make a note over here, ABC is greater than 0. That way when we multiply by ABC, it's not going to create any problems. And in fact, I'm going to multiply by 2ABC, so I can get rid of the fractions as well. So this leaves me with b squared plus c squared minus a squared times c plus a squared plus c squared minus b squared times, hold on, this should be a, this should be b, and then this should be c times c less than or equal to 3abc. And then we can just write rearranging, we get, and then we can just write down the problem statement. So looks like that. So let's just copy it down. A squared times b plus c minus a, oops, plus b squared times a plus c minus b plus c squared times a plus b minus c less than or equal to 3abc. And that would conclude the proof. All right, make sure to like and subscribe, and happy solving!